I'll begin with a word of prayer. Heavenly Father, we thank you for this day again, Lord. Thank you for these students. Please help us to use this time wisely just to answer a few questions about abstract algebra. In your name I pray, Lord Jesus. Amen. All right, guys. So what you got? Questions? You'll be proud of me. I was actually working on putting together the solution to Mission 9 today. But then I got distracted by other things. I'm not done yet, but I'm getting there. Which one? 5.1, number 15. All right. Ooh, I think I've done that one in class. Yeah. But that's worth writing down, that we have done that in class, perhaps. Section 5.1, number 15. We're supposed to show 1 plus the square root of minus 3 is irreducible in the square bracket m minus 3, but is not prime. Yeah, so that one, I spent the better part of 10 minutes working on that one. So look at the norm and analyze it and so forth.
Next question.
Yeah.
5.2, number 19.
Let's see, if A squiggle B, number 19?
Yes.
Okay. If A squiggle B in the Euclidean domain R show that delta of A equal to delta of B. Hey, what's up?
Are you going to be here for a while?
Till about 6, yeah?
Oh.
Do you want me to stop at your office when I'm done?
That's okay. I'll probably take off. I'm going to work on this some more this evening.
Do what?
Dr. Sperna, does this convince you to move our test to next Tuesday? You see how hard I'm working in this class?
Yes, but you always work hard. So
Yeah, but
That's nothing new.
you're gonna kill me on
That's-
Wednesday.
That's so nasty. Like,
I know.
so because she always works hard, that doesn't count for her.
It's
Because
like
it's just ordinary for her.
That's right.
Huh. That's an interesting principle.
So I need to start working less hard.
Not in my class.
Well, you know, I would work harder if the test was on Tuesday. I'm still trying.
When's the test?
Their test
The
is
day after yours.
Ah.
Well, you did it last time. You did fine.
I could push the test to
Yeah,
I could put the test tomorrow.
Tomorrow?
Sure, I mean, I can push the test up.
Yeah, that's
We'll call it Emily's test.
that's not going to help at all.
No, see, I'm asking him to move his back to the ball.
Ah.
Yeah.
Hmm.
I'm trying real hard, but it's not really getting anywhere.
Yeah, I don't think so. Are you going to come in early tomorrow? I mean, I've got class before anyway, but we can come in.
I'll try to be up there. I always have students in office hours right up until convo, unfortunately. But I'll try to make them go away so I can come talk to you.
But anyway, I'll see you tomorrow.
Yeah. Now, this problem would be totally, totally trivial if we had a norm. Right? This means that A and B are associates, right? So A is equal to BU for some unit. Right? So if I had a norm, like your problem 21, then this would be just utterly trivial because the norm of A would be equal to the norm of BU, and then that would be norm of B times norm of U, because norms are multiplicative in our language. And the norm of a unit we discussed as 1, so that would be the norm of B, and then we'd be like, yay, done, right? In fact, this is the technology that we used to prove that 1 plus root minus 3 was irreducible, but not prime in z adjoint square root of minus 3. But we're not in that world. We are in the world of Euclidean domains, where we have this divisor function with all the rights and privileges thereon too. So what is the thing that makes delta delta? We have that for A and B not equal to 0, I think. Delta of AB is what?
Greater than or equal to delta of A.
Okay. Greater than or equal to delta of A, right? Let's see here. Now, if U is a unit, right? Let's see, well, let's play some other games here. If U is a unit, then U times U inverse is equal to 1, right? So that tells me that neither of these can't be 0, obviously. So delta of U inverse, which is equal to delta of 1, right? Has to be greater than or equal to delta of U, right?
Is delta of 1 1?
That's not, I don't think that's part of the definition. Could we prove it has to be 1, though? Maybe we could. See, because we also have that delta of U times 1 is delta of U, right? What's that? The greater than or equal to what?
And delta of 1.
Yeah, we could put delta of 1 there.
So then that'd be
Woohoo! Yes. So. And also, okay, so delta of 1 is equal to delta. Okay, great. So I was going to say that they're equal to 1, but I guess I don't. I guess that doesn't have to be the case. I don't have enough experience with this divisor function as opposed to norm. I have just a little bit of intuition for the norm idea. I don't have much, if any, for the divisor just yet. I don't clearly understand what game they're. I mean, I haven't sat and really tried to logically understand precisely the difference. I mean, I know that the divisor function is not multiplicative, but okay. Anyway, we have that. So was that? I think that's probably going to be useful for this problem, right? I think we could pretty much play the same game with A and B, right? Like, no? So we have delta of AB let's see here. Oh, yeah, I'm sorry. Maybe I should be looking at delta of BU. Yeah. Delta of A equals to delta of BU.
Can you break up A again?
Which is greater than or equal to what?
Greater than or equal to either delta. Oh, I guess we should use delta of U.
Okay.
We just need the.
I mean, I want to show delta of A is less than or equal to delta of B, and also that delta of B is less than or equal to delta of A.
Okay.
I think that's our goal, is to show both inequalities and hence equality. Because I don't know how, I have no other access to equality here except through showing both inequalities, it seems to me. with the setup of the divisor function. We don't have like divisor functions equal to something, right? We just have it. It's got this kind of Weasley inequality that it. I shouldn't speak too ill of the divisor function. So sorry. But so we have delta of A is greater than delta of U, right? Which, by the way, is equal to delta of 1. And on the other hand, what's delta of B is, I don't know. I got so many different options here. I don't know what to do. And I'm sure somebody watching this probably can be shouting at me saying, obviously you do blah.
We know that U inverse, or delta of U inverse is equal to delta of 1.
Also,
So
you
I
want,
guess we can use the same.
you want me to trade B for AU inverse? That was what I was thinking about doing that. And then that's greater than or equal to delta of U inverse, which is also equal to delta of 1. So we have both A and B are... But maybe I should keep the A instead of the U inverse here. What'd that do for me? Because I could do that too, you know. That would give me the delta. I mean, that's one of the things I want is that delta of B is greater than... Oh, yeah, we should just do it both ways, right? So, yeah, delta. So delta of A. Yeah. I'm making... This was... I'm sorry, this was my great distraction to you guys, really, right? I mean, we should just set our hearts on, we want delta of A less than or equal to delta of B, and delta of B less than or equal to delta of A. And with those two goals in mind, you clearly should just write down delta of A equal to delta of BU, which is less than or equal to, less than? I've already forgotten. Grief. Greater than or equal to delta of B, but delta of B is equal to delta of AU inverse, which is greater than or equal to delta of A. So, consequently, they're equal. There. Sorry, I took us on a kind of sideshow. As you can see, there's another homework problem you could work to show that the valuation map. I'm sorry. Yeah, well, I think Sperano tends to call this the valuation map, but Nicholson calls it the divisor. So the divisor map is constant on units.
Yeah, that's an example.
Oh, okay. As I have warned you guys, I have not digested the sections in Nicholson yet, you know, so I set my sights on trying to communicate to you all of my notes on this material. Then my next goal was to go through Nicholson and pick up the pieces. So like I need to go back to chapter 4 and like fill in gaps that I missed. And, but then again, I'm debating on whether I should do that or if I should continue with the story we were doing last time and say a little bit more about ideals. I haven't decided yet. When do I lecture next? Oh yeah, tomorrow. Well, we'll see what happens. Oh, okay, next. Move along.
I guess we could do 21 for the same section.
21, all right. .2, number 21. Let B be non-zero in R, a Euclidean domain show B is a non-unit, excuse me, if and only if delta of AB is greater than delta of A for all A not equal to 0 in R. I guess if I did these homework problems, maybe I'd have more intuition for what the divisor function is. In fact, that is probably why I assigned these. So, wow. So I kind of prefer to say, rather than saying this, to say B is not a unit, just to be clear. I mean, I am certainly guilty of making up various words, various points, but just to be sure we all understand. All right, so I guess, excuse me. So should we try this direction, perhaps? So B is a non-unit. And R is a Euclidean domain. I guess it doesn't tell me anything much particular except that there does not exist let's say R in R such that what? Yeah. And all right, so that's the data. And now to prove an inequality like that, what should we set our sights on proving? I mean, you want to show this, right?
To show that they're not equal. We already know that it's greater than or equal to, by definition.
Okay. Let's start by writing that. We know. That's a good starting point. Delta of AB is greater than or equal to delta of A for all A not equal to 0. Well, let's see here. If B,
It says B not equal to 0.
oh, it says, okay, oh, good.
Yeah, so
Great. Thus, it suffices to what?
prove it's not equal.
Right, prove that delta of A, B is not equal to delta of A. So usual way to probably to do that would be to suppose they're equal and look for a contradiction. Towards contradiction, assume delta of AB is equal to delta of A.
It says for a hint, use exercises 19 and 20, which we just did 19, and 20 is just the opposite. I don't know if that helps us with the forward implication or if it's in here for the other way.
So 20 says that if A divides B and they have equal divisors, delta of A is equal to delta of B, in a Euclidean domain, then A is associated to B. Certainly, these homework problems are nice. They really do help us understand what this pesky delta is. But, well, Well, we also know that this is less than or equal to what? I'm sorry. Yes.
Yeah,
An idiot. Greater than or equal to
delta
delta
B.
B, right? Or A. Hmm. Why does that say?
Wait, if delta of AB is equal to delta of A, does that mean that they're associates? Is that what we just showed?
Delta.
No, that'd be number 20, so we need that A divided B to use that.
Hmm.
Oh, yeah.
What?
Well, if that's true, then the A and A, so you're saying A and A B are then associates?
Yeah, but I don't know if we can use that because we don't know that A divides B.
But no, but then you would just say A divides AB, right?
Oh, okay, yeah.
But like B is a non-unit, so.
Okay, so we have,
Okay.
we know A divides AB, right?
Consider A divides AB. Okay.
And then by exercise 20, that implies that AB is associated to A, right?
Yeah, I mean, whatever.
Yeah.
Okay, so then we know that AB is equal to AU for some unit.
Wait, just,
Is that what the definition is?
just let's see here. How do I know that if delta of A is equal to? So this is playing the role of A, right?
Right.
This is playing the role of B.
AB equals AU, right? For some unit.
Yeah, this forces B to be a unit.
You're
But
right.
it can't be a unit, right?
Yeah,
So that's our
That's
contradiction.
a contradiction.
yeah.
Okay.
This implies B is a unit, which is a contradiction. Yeah. Now, if you want me to prove that, to say that these are associates, that means that AB is equal to A times U for some U. But we're in an integral domain, so we have cancellation. Remember, Euclidean domain, PID, UFD, these are all integral domains. They're integral domains with various structures, which are interrelated, but not interchangeable.
Okay, so we can cancel, so that means B equals U.
Right, which is a contradiction. Now, so that's that direction. How about the other direction? So suppose that delta of AB is greater than delta of A for all A not equal to 0 in R. And then we suppose B is a unit, right?
Towards contradiction.
Yeah. Hence, well, I think it's A divides AB, right? Or maybe B divides?
Wait, what?
B divides AB? B is a unit, right?
Oh, yeah, we just saw that.
So by exercise 20, we get the delta of B equals delta of AB, which is a contradiction, of course, to you. So I guess I should have signed number 20. Apparently, that's where all the action's at.
That's
Yeah,
not
so-
our revision.
Oh, okay, good.
Yeah, so you did.
Woohoo!
That's why I asked 19, because I thought it would help.
So maybe, did it help? I'm not sure if it did.
I don't know, I haven't looked at 20 yet, I just,
Okay.
it's like, oh, they're very similar. But
Yeah.
I'd say that both of these, at least using it should help prove it.
I think so. At a minimum, after we have played with all these, we should at least have a deeper sense of what this pesky delta is. Now, Esperanto said what he does is a lot of times he'll ask the students to actually prove a specific delta, which he gives them, is actually a evaluation on z adjoint square root of -2. So I showed you guys pictures and a proof of that from my number theory notes, but if you were in Esperanto's, you'd get to prove it for yourself, I guess. But I think that's probably, in all likelihood, I'm pretty sure he's talking about 422. What excitement is this? Yes. Sorry. Hamburgers. Anyway, I have been told to get soda, so this is very exciting. All right. Next.
Could we, like, draw a diagram with all of the, like, Euclidean domains and, like, PIDs and what everything is?
Sure.
Like, I think that'd be helpful.
I could try.
Okay. Starting, like, back with,
Like every domain, like starting
Yeah.
rings, just
start,
all the different domains. and how
just
they
like,
play into-
all of the big
all
square,
of it.
yes.
Now start with the big box,
We're gonna need more room, there we go.
Fields, integral domains, all of it.
All right, so this is rings.
Okay.
Okay. Actually, general rings.
Oh yeah, we could do commutative rings theory.
Yeah. General rings. And then of the Denier rings. So here,
So general rings have no identity, right?
one not an element of R possible. Well, let's say one's not an element of R. These are also general rings, if that makes sense. So the big box is general rings.
Okay.
And then, of course, commutative.
Integral domain?
Commutative rings. Of course, you can have general commutative rings up here. Here you have things without unity and which are possibly non-commutative. Let's see here. Then what do we have? So we got
Domain?
commutative
Or
rings.
just domain?
Yeah. So a domain. That's a good question. Domain. Let's see. What's a domain?
I can never find that definition. Like, the definition of field, I can never find in this textbook.
Ah.
And it's with integral domain.
A domain is it doesn't have to be commutative,
Yeah, domains are just,
but I think one is in there.
Oh,
So maybe in my current way of drawing things, maybe I should. I at some point I'm going to get into trouble with this picture, but I believe domain would be something along the lines of this in my current picture.
yeah, it says, yeah, a domain is just non-zero
So
supervisors.
here we got integral domains. Integral domains. And then over here, domains. in my current picture. This is possibly non-commutative, you know. So, but what is a domain is something where we don't have zero divisors.
Okay. And we also have cancellation now, right?
Yeah, and then there's an exercise which shows the equivalence between not having zero divisors, having cancellation. It's like there's a 3.
Yeah, it's a theorem. It has.
Let me be more
Yeah, you have on
specific.
the left, cancellation and right.
Where is?
Theorem 1 of 3.2, page 171.
Yeah, because he doesn't stick with domains very long, but right. These theorem, yeah, like you said, theorem 1 on page 171, AB equals to 0 in a ring if and only if then either A or B is 0, or if we can right cancel or if we can left cancel. These three are equivalent. These conditions are equivalent. And I think on the next page he says a ring R is called a domain if any one of those three conditions is satisfied. In other words, a domain is a ring in which you either have left, right, either left or right cancellation property, or you have no zero divisors. By the way, those three things are equivalent. So if you have got one, you got the other two. And if that's the case, then we said it's a domain. If it, in addition, is commutative, then it's an integral domain. Then, let's see. Then inside integral domains, we have, we have fields. I'm not sure where I think a field would, I feel like a field is probably down in the corner here, if I had to guess. That's a little bit dangerous for me to draw in my picture at the moment because I'm trying to descend from less structure to more structure. I feel like that's jumping ahead to a lot of structure, right?
What's the difference between a field and an integral domain?
A field is, what that means is that if A is not equal to 0, then A inverse exists.
Oh, right. Okay.
So a field is a commutative domain in which every non-zero element is a unit. Or you could say it's an integral domain in which every non-zero element is a unit. So examples of something which is an integral domain but is not a field would be the integers, most notably. Right? Lots of, no zero divisors, right? But, okay, so then we want to think about, let me just write it up here. I have, what's the equivalence we did, what was the story last time?
So, first is Euclidean domain.
Right, we have Euclidean domain, we have principal ideal domain, and we have UFD, unique factorization domain. This is all happening inside the integral domain box.
But not necessarily inside the field box.
Right.
Really? Okay.
Yeah, none of these have to be fields.
But they can be?
Yes, I think so. So I believe in my picture, the way I would illustrate that would be to draw yet another line like that, right? But that's still no, I can't do that though. I got to take this field off. I'm not sure where the field goes because the thing is, the pesky thing, I'm not sure how, you've put me in a pickle. I'm not sure how to, this I know is not the case, right? So it's,
your field wouldn't be able to go up.
I don't think I can just say, well, the smallest one is Euclid. Yes, right. Thank you. I'm just thinking of it backwards. So this is the UFD. Then, inside that, I have PIDs. And then inside that, I have special PIDs called Euclidean domains. Well, you know, I'm not sure how to draw a field in this picture now that you ask me a question like this.
Can every single one of those?
I gotta think about it. Let's think about it. Is a
Okay, a UFD is, they have to have a unique.
I think some of these some of what we're asking. Let's just take something specific, real numbers. It's kind of an awful field. What's prime in the reals? Is 2 prime in the reals, though? What does it mean to be prime? I'm not sure. I'm not disagreeing with you. I'm just asking us to really think through our definition of prime.
Prime means that the only divisors are the units. Is that what we said last? Because like if our units are 1, -1, I, and -I.
Let's look it up.
Okay.
That was 5.2, right?
I'm not sure.
Might have been 5.1. Let's see here. Where are you? Yep, there we go. An element P of an integral domain R is called a prime, and it's said to be prime in R, if it satisfies the following conditions. P is not equal to 0, and P is not a unit. Okay, is 2 prime? Well, 2 is not equal to 0, but 2 inverse is 1/2, and that's a real number. In fact, if you think about replacing this with A in a field, F, if A is not equal to 0, then
So immediately, so there are no primes in a field.
yeah. Right.
So what does the prime have to do? What do we need primes?
Well, primes, I think, are most interesting when we're outside the context of a field. Primes are more interesting when not everything is a unit. Everything non-zero being a unit is a pretty special context, I suppose. I mean, there are a lot of ways to get to that context from other things. I mean, we have various theorems, like if we have, for example, I think this is one of their theorems, right? If we have integral domain I, D, let's say, then integral domain polynomials, if D is an integral domain, okay? I think one of the theorems we had was that the polynomials built over an integral domain, are they also an integral domain? Certainly if we have polynomials, I know that polynomials with coefficients from a field form an integral domain. Is it the case that if we have polynomials from an integral domain, that is itself an integral domain? Yeah, we can just kind of test ourselves on that. If you have, I think the zero divisor, if I have a0 plus a1x plus, dot, 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 and I multiply that by b0 plus b1x plus dot, 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 and that's equal to 0. Well, amongst these, I have a0, b0 plus higher order stuff, right? But the only way that's equal in the ring of polynomials is if it's equal coefficient by coefficient, which says in particular that a sub 0, b sub 0 has to be 0, which means that, well, I should be careful. That doesn't, That's not the one I need to be looking at. I need to be looking at the I think the proof was by the leading terms, not the constant terms. You could have constant terms being 0 in a non-zero polynomial. It doesn't really tell me anything. I should look at the leading coefficients, right? I should look at like a to the n, x to the n. In fact, now I'm starting to remember doing this with you guys. B to the m, or at least writing it out for myself. I'm not sure which. Sometimes I forget about what I've done with you guys versus what I've written on a piece of paper for myself, you know. So that's an, bm, x to the n plus m, right? In order for the polynomial to be 0, you'd need to have, how to say this? There's some fussier argument needs to be given here. I'm not convinced. I'm pretty convinced it's true. I'm not convinced that this is a proof of it either. All right. We must have proved that somewhere, right?
I don't think so,
Sorry.
we have if F is a field of polynomials over F, or a PID.
Mm-hmm. Yeah, polynomials over a field form PID. That is proved that somewhat recently.
Yeah, it was just a couple of, maybe right before.
Yeah. It may just be that it wasn't interesting to say when we would have said it, you know. Feels like it might be something that was said in section 4.1 somewhere, but I don't know. I guess if it's false, it'll probably be a question on your test. Or will it? Got all kinds of fancier theorems. I feel like I proved that somewhere. For the life of me, I can't remember. Well, maybe I'll... see, I got this theorem 3 on page 232 about polynomials over a field. That's great, but that's not what we're fussing about at the moment. Well, I'm not totally sure that... I mean, I know it's true. It's definitely true that if D is a field, then f of x is an integral domain. So certainly that's one important way of creating integral domains is from looking at polynomials over a field. Conversely, an important way of creating fields is taking, polynomials and quotienting by maximal ideals, right? How do you form a maximal ideal? Usually, a lot of times, by the principal ideal generated by an irreducible polynomial, right? An irreducible polynomial gives us a maximal ideal, and then if we take polynomials mod a maximal ideal, that gives us a field. If we, on the other hand, a little bit weaker, if we just mod by a prime ideal, then we just get an integral domain, right? That, like your first problem, the first problem in mission 9 was kind of about that a little bit. It's not quite that, it's a little bit more interesting than that, but. So anyway, in short, unique factorization domain, like I don't know if that makes sense for a field, does it? I mean,
Does the field have a division algorithm?
a UFD says what? It says, what's a UFD? What's the definition? Yeah, it says something, but how does it? The word, the fine print matters here. You know what I mean? Every non-zero non-unit in R is a product of irreducibles. Right? So I guess a field is a UFD by the fact that it vacuously satisfies these conditions. There are no non-zero non-units, so it can't not be a UFD.
Yeah, okay.
So if a field is, in some sense, stupidly a UFD, is a field a PID? Is every ideal? What is an ideal?
Wait, so a UFD
What are the
is a field, though?
Yeah, UFD does not have to be a field, but a field is a UFD. What about a field? Is it a PID? Is every ideal in a field a principal ideal? Is it generated by a single element? Well, I think so, because if you look at an ideal in a field, it's either 0, right, or it contains a non-zero element, which is a unit, which means it's the whole thing. So the ideals of a field are 0 in itself.
Oh, okay.
So
Vacuously kind of.
it's either generated, the ideal is either generated by 0, or it's generated by, pick it, anything. So yeah, a field is a PID in a stupid kind of way. And is a field a Euclidean domain? Yeah, that's. I mean, I don't know. Maybe in a stupid sense that's automatically true. I mean, a division algorithm is sort of a device for dividing. You can naturally divide in fields. So it wouldn't be surprising to me if we look carefully at the definition of Euclidean domain, if we can, through some sort of really stupid choice of some very, very silly definition of delta, say that it's a field. The field is the Euclidean domain. But I'm not as certain about that. I should think more about that. So I'm not, but certainly. So I mean, I guess I'm kind of getting myself into the place where maybe I want to put field down in that corner. Yeah. So I guess I'll put field down here, but I'm gonna put a little. I'm a little wishy-washy on that last point. I haven't constructed the delta. I'm not entirely sure about that. Are there any other structures we've talked about?
That's what I was trying to think.
Division, a division ring.
Wait, is a division ring a field?
A division ring would require us to make this, we need to take this picture and bend it like this. Division rings are like over here. But they're also, connect this point to this point. Okay. Connect this point to this point. Division. So a division ring is a ring in which we have a way to, every non-zero thing is a unit. However, there's no assumption of commutative. So if you throw in commutative, then a division ring is a field. In the case things are finite, some of these things simplify further. Like you can't have, what is it? I believe a finite integral domain is automatically a what? I think so. Yeah, theorem 3 on page 173. Every finite integral domain is a field. And the argument for that is really, it's really quite nice. And it's the same argument which has been given for like 2 or 3 other things. Page 173 in Nicholson. You basically, you take it's this typical finite argument. You list the elements in the ring, and then just basically argue by process of elimination that there has to be the inverse of the other one in there if you just look at, well, you see what the argument is here. What does he do? Takes the ring, lists everything in it, picks a non-zero element, multiplies everything in it by that non-zero element. But hey, the identity is somewhere in there, which means that you've got A times R equals to 1, which is, inverse. Ooh. That's essentially the argument. I mean, to make that gel, you need that it's an integral domain. That forbids things like Z mod 6, which is finite, but not an integral domain, and hence not a field. I mean, we've done other things, of course, playing with the group of units and the interplay between this and group theory. We've talked about, how quotients work. Again, integral domain. Well, let's see here. How's it? Now I've lost my train of thought. We talked about modding by prime or maximal ideals, which give us integral domains or fields, respectively. And I'm trying to remember what we have to mod by, though. I think we have to mod an integral domain. That can't be right. It should be a commutative ring. I think a commutative ring mod a prime ideal is an integral domain. For example, if we take Z mod 6 and we mod by a prime ideal, which I think would be like 2Z6 or 3Z6, that will leave us either with something isomorphic to Z mod 2 or Z mod 3, both of which are finite integral domains and hence fields. So, yeah. So that tells us one thing, is to appreciate the sort of the nuance between modding by prime and modding by maximal. We're only going to really appreciate that, the distinction in infinite cases, I think. Because the finite integral domain is automatically a field. Yeah. I think that's it. Very good question, I think.
That helps me visualize.
Oh, yeah. This is something